Swayam Prabha. Digital India. Educated India.
So, in the last class we looked at the basics of 2D NMR, heteronuclear NMR spectroscopy, and we started with the HSQC experiment. HSQC stands for heteronuclear single quantum coherence. So, we will continue with that today and see how this experiment works, what kind of the pattern of peaks we can expect to see in this 2-dimensional experiment. So, the shown here is the 2D pulse sequence which we started with yesterday. So, here you can see this is a sequence of pulses which are applied on the proton channel. Okay. So, we saw that yesterday that we defined two separate channels, one is called proton, another is called carbon, and on the proton side we apply a series of pulses and delays. So, there is a very specific values of the delays which we will see more in detail today, and similarly on the carbon channel we apply pulses. So, here this pulse which is narrow, which is a narrow rectangle, is a 90-degree pulse. So, everywhere here you see it is 90-degree pulse, whereas this fat rectangle is called as a 180-degree pulse. So, this 90 and 180 you remember is the flip angle, the angle by which the magnetization rotates from z axis to y, and this is from z to minus z. Or yesterday we defined two different, in the last class we looked at two different types of pulses. One is called inversion pulse and refocusing. So, inversion is basically taking magnetization from z to minus z, whereas a refocusing pulse is takes the magnetization from x to minus x or y to minus y. So, this is a definition of a refocusing pulse. So, basically a 2-dimensional experiment HSQC consists of a series of or a number of pulses applied like this with a specific delay or difference, a delay value, a delay period in between. So, the first part of the sequence, which is this portion, we call it as inept. So, inept is something we saw in the last class, is basically a method to enhance the polarization of a insensitive nuclei, which is carbon here, by transferring it from proton. So, this is achieved using this particular series of pulses, this particular block, and we use the word inept block. So, after this pulse is applied, after this inept is applied, here at this point, after this pulse on carbon is applied, this here at this point the carbon comes to the xy plane. Once carbon comes to the xy plane, then during this whole period from here to here, we allow the carbon chemical shift to evolve meaning we allow the FID of carbon to start. But remember, this is an indirect dimension. So, we are not going to physically capture the signal, this is not a detection, it is indirect detection. So, similar to all the 2Ds we have seen so far, the idea is you allow the chemical shift to go on. And after this period, at this point, now what we do is we go back to the hydrogen proton, because we have come from proton, we come to carbon during this part, and from here we go back to proton and then detect the proton magnetization. Okay. So, this is what the idea is that we saw in the last classes, that the idea is to start from hydrogen, excite an hydrogen atom nucleus sorry, and then transfer the polarization to carbon, and then reverse come back to hydrogen, transfer and detect the hydrogen. So, this is the most optimal way to achieve the best sensitivity. So, you start from a hydrogen, come back to hydrogen. So, this is how all NMR experiments, many of them are typically designed so that you gain maximum sensitivity, and therefore, you do not even if the natural abundance of carbon is low, at least you have taken advantage of the high gamma value of proton. And now, let us look at each of these details, or let us see how the magnetization mathematically goes through this pulse sequence. So, this is how it is shown like here. So, you start, so we are looking at a carbon proton pair, Okay. So, we are looking at a system like this where one hydrogen is attached to directly through one bond. So, this is one bond to carbon. So, our aim in this whole exercise, in this whole experiment is to correlate the chemical shift of this proton with the chemical shift of the directly attached carbon. So, that is our aim in all these experiments. So, we are correlating hydrogen and carbon. So, we start from a proton pulse, that is this pulse here, and we have applied a 90-degree pulse, the first pulse on proton, then the proton comes to xy plane, but we do some inept experiment here, inept block here, because of which the carbon polarization has now gone to carbon. So, we are not going to go in details of a mathematical analysis of how this inept works, that will be not covered here, but we will have to take it for granted that proton polarization is transferred to carbon at the end of this period. Now, during this period, which is now labeled as T1. So, you see here you have a T1 by 2, that is half of T1 and another half here, and between them is one 180-degree pulse on the hydrogen. And why is this here? The reason for this is that during this period when the carbon is free to evolve because of its chemical shift, during this period it will be coupled to protons because by J coupling, because that is what is here. So, we are exploiting the J coupling to in the first place to get the transfer by inept. So, remember inept works by using J coupling between two atoms. So, here during this period when it is evolving, it will be coupled to the hydrogen. So, to avoid that, that is to decouple protons from carbon, when carbon is evolving, we apply a 180-degree pulse on the proton in the center of the evolution time. So, you see here this is symmetrical, there is half T1 this side, half T1 this side. So, right in the center is applied this pulse. So, during this period the carbon chemical shift has a evolution. Okay. This is again similar to many 2D experiments we have seen earlier, where in the indirect dimension, that is during the T1 dimension, we have a chemical shift. Then you transfer back to proton during this period, that is reverse inept. So, it is exactly a reverse of what you get here. So, that is why if you look at the picture, they are very symmetrical. So, if I for example draw a line here at the center, if I draw a line, it is exactly symmetrical. So, it is a reverse of the inept here. So, when I after the end of this reverse process, now the proton magnetization is on the xy plane, and during that period it starts evolving. So, as you can see here, there is a chemical shift of hydrogen which is captured during the T2 period, T2 evolution. So, now if you look at the whole picture in total, what we have achieved is that we have achieved a transfer of magnetization from hydrogen to carbon, got the chemical shift of carbon, went back to proton and got the chemical shift of proton. So, what we have done, we have correlated or connected two atoms here, one is hydrogen and is carbon. So, therefore, when I do a Fourier transform of this combined signal, which is now T1 and T2, I would expect a 2D spectrum where the carbon and proton are correlated. So, now this is just a little bit of detail, a technical detail which we can see is that what is the value of this delay period. So, this is delay period as it is shown here, it is 1 over 4 times into j. So, that means this is 1 over 4 times j and this is also 1 times j. So, the total period from this pulse to this pulse is going to be 1 over 2 times j, double of each period here. So, typically what is done is this period 1 over 4 times j is chosen, j depends, now j is shown here, this is an approximate value, this is for a hydrogen proton connection pair, direct connection from sp3 carbon going all the way to sp carbon. So, we saw that in the previous classes that the coupling constant is weak for CH one bond, that is CH, that is sp3, and as you go to sp2 and that is in aromatic, and sp in acetylene for example, the coupling constant is very high. So, this is a large variation you can see here. So, what one does is based on what type of functional group you are trying to look at, then you decide the delay value. So, for example, you are only interested in aliphatic, meaning only sp3 carbons, then your value can be somewhere around 140. So, for that value you choose a delay accordingly. So, 1 over 4 into 140 into 2. So, if you want to look at sp aromatic systems, in aromatic you then tune your J your coupling will not be 140, it will be around 160 to 180. So, if you choose that value accordingly J value, this delay value will change. So, typically the delay which we use is about this much time, 2.5 to 3.5 millisecond coming from this pulse what is here to this side here. So, we are looking at the entire delay period between these two pulses. So, this is why is it important to know this? This is from a practical aspect, because you want to sense the maximum sensitivity is obtained when you achieve a 100% transfer. So, now coming back to the concept of transfer, efficiency of transfer, if you recollect we saw in the hydrogen proton spectrum, you will never get 100% transfer from one proton to another proton in any experiment, typically even if you use COSY, NOSY, TOXY and so on. The efficiency is not 100%, typically it is, in fact in NOSY it is just about few percent, 5 to 10%, not even 10. So, you see the efficiency of transfer is low when it comes to proton transfer, but when it comes to proton carbon transfer the efficiency is high. The reason being that we use this experiment a block known as INEPT, and that has heteronuclear transfer is 100%, can be 100% of course, again not ideally 100%, but not practically it will, but you can reach a level of 90% efficiency provided you take the correct values of these delays. If you choose incorrect values, then efficiency goes down tremendously. So, that is why one has to know what type of systems we are looking at. Therefore, one should know have a rough idea of what are the coupling values you expect, and accordingly you have to decide the delay between the pulses. So, this idea at HSQC whatever we discuss right now is applicable to many 2D experiments in heteronuclear NMR in general. So, that is why we spend more time on this experiment to understand what are the integrities of these experiments. So, one thing which we discussed yesterday again was decoupling, is that when you are acquiring or detecting protons during this period you have to decouple it from the carbon, because carbon is what is coupled to proton by J coupling. Now, one has to keep in mind the following. So, let me show you one thing which is very important to know here, is that we are now so we have in a molecule we have this combination and this combination. Okay. So, basically this is about 99%, because the natural abundance of C12 is 99% and this is 1%. Okay. So, this is, so our whole experiment is based on detecting this much, this quantity, this moiety, because remember carbon 12 is NMR inactive. So, we are only, this is not possible to detect because there is no way to get C12, it is not active NMR active nucleus. So, the only thing we are looking at is carbon to 13C, but in this experiment therefore, what we are looking at is only signals from 1% of the sample. So, during this period you see we have to decouple C13 because 1H is getting detected. So, whenever you are detecting 1H you have to decouple carbon 13 because this anyway is gone, we are not looking at this. Similarly, when you are evolving carbon here in this period we should decouple from proton. So, that is what is this pulse. So, therefore, in both T1 and T2 we apply decoupling. Okay. But again going to little more deeper, this decoupling is slightly different from this type of decoupling. This is just one pulse. Okay. So, this is just one 180 degree pulse, which is achieving the decoupling. But here it is a series of 180 and not simple 180, it is not just one pulse. So, this is that's why we show it in a box like this. Okay. So, this is called composite pulse decoupling. CPD is used for the word when you apply decoupling like this, and this is simple 180 degree decoupling pulse. So, this experiment captures many of the details of a typical heteronuclear NMR. In fact, although we are not going to do this in this course, you can also use these ideas to design a 3-dimensional experiment, an n-dimensional experiment, because these blocks what we are seeing are called building blocks. So, you can actually build n number of blocks you can put and choose depending on what experiment you are doing, you can design new experiments. We will see one such 2D experiment. We are not going to go into 3D in this entire course, but we will look at in a 3D experiment where we will combine the idea of this with a 2D homonuclear experiment. So, let us continue now to see how the spectrum will look like now that we have understood how the experiment works. So, this is the HSQC spectrum of this molecule glutamine. It is an amino acid and it has a structure which looks like this. So, there are how many pairs of hydrogen carbon. So, you have to keep in mind that we are only detecting pairs, we are not detecting any other system, we are only looking at CH pairs. So, there is one CH here, there is one CH here and there is one CH here. So, we will assume that these two are equivalent and we will assume that these two are equivalent, but you have to keep in mind that it is not so. The reason is this is a chiral carbon, this carbon which is shown here is a chiral carbon. So, whenever you have a chiral carbon in your molecule, it is asymmetric, means you have a R combination or you can have a S combination, S isomer or R enantiomer. So, we are looking at L amino acid in general. So, this is typically an L amino acid which is there in our chemistry and biology we use. So, therefore, this is only one enantiomer, it is asymmetric. So, moment you have an asymmetry in your molecule, it need not be only its geometrical symmetry, but even this symmetry makes all the hydrogens inequivalent. Remember, we saw the chemical equivalence concept. The idea was that if there is a symmetry in the molecule, then there is a chance of equivalence, chemical equivalence, but there is no symmetry here, it is a very asymmetric system because of this chiral center here. Therefore, these two hydrogens are actually not equivalent chemically and these are also chemically not equivalent. What it means is that these two hydrogens will have two different chemical shift values, but they may be very close to each other. In fact, they may be even overlapping, means they may have the same value, but having chemical shift same is not that they are chemically equivalent. Okay, they are same because they are accidentally close in environment, chemical environment, and therefore, they show up to same. So, therefore, in this whole analysis in HSQC, we will assume that the two chemical shifts are same, but they are not necessarily chemical equivalent. So, therefore, you see we have only see one peak, we do not see two peaks for each hydrogen. So, now let us understand how this spectrum can be interpreted. So, on this axis, y axis is your carbon chemical shift, as you can see the values, and on the x axis is the chemical shift of hydrogen. So, we are only looking at CH system. So, we are only having 3 such 3S system and therefore, there are 3 peaks here. Now, let us see how to look at the positions. So, now if you look at this pair, this is attached to 2 electronegative functional groups, one is carboxylate and other is NH3. So, therefore, this comes downfield shifted for both proton and carbon, and therefore, the carbon value is close to 60 ppm and proton value is downfield shifted to 3 to 4 ppm. So, if you look at individual 1D and carbon, if you recollect our 1D proton and carbon NMR part in this course, we saw that if there is a carbon attached to an electronegative group or a hydrogen attached to carbon which is attached to electronegative, they come downfield shifted because of the shielding, de-shielding effect. Now, let us move to the second one. This is CH2 and this is now coming in the center. The reason being, we will look at it, this is an aliphatic spin system. So, there is shielded like we saw the inductive effect. So, it is upfield shifted. But if you look at compared to this hydrogen carbon pair, here it is now amide. So, it is again an electronegative electron withdrawing functional group. And because of this pair comes now downfield shifted compared to this. Downfield means it is shifted down both in carbon and both in proton. So, you can see that this is why this CH pair comes downfield shifted and it is around 2.5. So, this is how the spectrum of a simple molecule like this will look like in HSQC. So, here the interpretation is not based on the J coupling and so on like we did in 1D, it is purely based on the knowledge of where the chemical shifts are expected to come, and that is how we can look at it. So, this HSQC is only telling you the peak positions. Okay. So, it is not giving you the information of proton-proton connectivity, which is can be obtained only from COSY. Okay. So, therefore, you see this experiment, it gives you some information, but to get the connection that this is this peak, this pair corresponds to this peak and this pair corresponds to this peak, that kind of information we have to obtain with some more experiments. Of course, from experience just now as we analyze, we can do that also, but a more detailed molecule structure, one has to not only rely on HSQC, one has to also combine this with other experiments, and we will see that when we come to the assignment part or the structure determination part of this course. Let us move on to another example, so that we can go through all different combinations, and you can see here that in this case, now this is again an amino acid, this is isoleucine. So, it has branch chain amino acid. Okay. So, here it has two chiral centers. So, this is also chiral, this carbon, and this carbon is also chiral. So, because of this it is achiral and both are L configuration. So, now let us start from looking at which peak can correspond to which of this CH. So, how many CH pairs do we have? We have one here, that is CH3 is H3, remember H3 always are equivalent. So, we have CH here, these two are not equivalent, but for the time being we will consider them as same chemical shift. So, we have one CH here, that is one here, this is second, this is the third system, third CH pair, another fourth and a fifth CH pair. Okay. So, this is actually the experimental spectrum recorded for this molecule. So, one can say that the most upfield shift, which is close to 10 ppm and around 1 ppm, has to be methyls according to our earlier analysis, where we saw that methyls are always upfield shifted. There are two methyls in this molecule. So, the second one is this methyl. Now, which is which methyl, how did we get that answer? Again, this is more or less based on kind of experience and database, means we will have known values for these amino acids, and one can, based on that, one can say that the most upfield is usually this methyl and the next upfield is this. One can always argue based on shielding, deshielding effects, but this is not how it is done. Typically, we have to assign this each and every peak to the respective pair based on more experiments. So, right now I am only showing you the results, means given a spectrum which how the peaks look, but how did we arrive at which peak is which, that is going to come later, where we look at more experiments. Now, this is a CH2, this comes here. So, you can see there are two peaks here, one peak is from one hydrogen and another peak is from another hydrogen. So, again we do not know which is which, these are called prochiral protons. So, this is right stereotopic protons, and you can see there are two protons here. So, two peaks, which one is which we do not know. So, we usually have to arbitrarily say that one of the peak is one proton, other peak is another proton. But the important point to note is that they are not equivalent. Many times you may think that because there is a CH2 here, it becomes equivalent, but that is not the case, it is non-equivalent. So, that is why there are two peaks. Now, coming to this peak here. Now, this peak we can go to this peak. So, there are two peaks left, one is this CH here and another is this CH. Now, if you look at this CH, similar to what we saw in the previous example in glutamine, this comes downfield shifted because it is attached to two electronegative groups. So, therefore, this downfield, this one down here will be most likely from and going to be from this. So, therefore, this one has to be this peak, okay, that is the beta carbon of isoleucine, and the alpha carbon, this is an alpha amino acid. So, this carbon is denoted as alpha, it has a peak which is coming here at this position, this is a downfield shift. So, this is how we can interpret or analyze the HSQC spectrum of molecules. Let us look at one more example before we move on to HMQC. So, this is a threonine amino acid called threonine, and here you can see that there are only 3 types of carbon proton pairs, one is this pair, one is this pair and one is this pair. So, again this is a alpha amino acid. So, like we saw in the previous 2 examples, this will come somewhere around 60 ppm, which we saw earlier. So, here also I can see a peak at 60 and that could be this peak. Now, methyls again remember comes upfield shifted, and therefore, here it will be somewhere around 1.5 to 1.8 or it is around 1.5 ppm. Okay. And this carbon, this is here the beta. So, this is alpha, beta, gamma. So, the beta carbon is directly attached to an oxygen. So, therefore, we expect a downfield shift because of that, and therefore, this beta carbon comes way down here where I am pointing the arrow at around 70 ppm, 65 to 70, and also the alpha is downfield shifted, sorry, the proton is downfield shifted and alpha is here and beta is here. So, let us assign now which is which. So, methyl is this peak upfield shifted, this CHOH is the downfield shifted, and the middle one is the CH alpha amino acid peak. So, let us look at some more example. This is on an aromatic amino acid. So, in the aromatic amino acid, now we have, so we are looking at different types of amino acids, and because the different functional groups are there, it will help us to look at where the peaks come in HSQC. So, if you look at this tyrosine molecule, then you have a CH pair here, there is a CH pair here, CH2, and there is many CH here. So, one is there is a CH here, this side and this side, there is CH here and here, and there is no CH here. So, now if you see, you may again think like we saw in the case of simple aromatic compounds, whether they are chemically equivalent, but these two are not chemically equivalent because there is a asymmetry here, this carbon which is chiral. But what happens is that this amino acid in a molecule rotates rapidly around this axis. So, let me show you that axis. There is typically a very fast rotation around this axis. Therefore, because of this fast rotation, these two hydrogens, that is the two hydrogens in the orthoprotons and the metaprotons are equivalent because of this rotation. It is similar to what we see in the case of methyls. But there have been research in this area where people have gone down to very low temperature and found that this ring freezes, means it does not rotate around this because of low temperature, and at that temperature people have seen that these two hydrogens, they become non-equivalent and they show different chemical shift. But we will in our case in a simple molecule like this, or even in proteins and peptides at room temperature, these rings rotate very fast. It is called ring flipping. So, the ring flipping occurs so fast that these two hydrogens are more or less averaged out like in a CH3 system, and they have chemical equivalent chemical shifts, I mean equivalent in that sense. So, now let us look at the different hydrogen carbon pairs. So, again as you can see in the spectrum, there are two peaks coming here which is around 30 ppm, there is one peak coming at 60. So, this is an alpha amino acid. So, again like in the previous example, this hydrogen carbon pair which is alpha carbon, is expected for this peak here, and the beta, that is this CH2, again they are not equivalent. So, they show two different peaks at 30 ppm, 35 ppm. And then aromatic portion, remember we saw in the hydrogen proton NMR, it comes around 7 to 7.5 and the carbon comes around 120, and that is what we are seeing here in this portion of the spectrum. So, it is very now easy to assign which is which. This CH is this peak because of this downfield shifted, the CH2s are these two hydrogens protons, and then the aromatic one is upfield shifted, and the second one which is downfield shifted is this because of close to this hydroxyl group. So, we expect two equivalents, one pair here, another pair here, and that is what is shown here. Okay. So, we can see like this, so we have covered different types of amino acids and different type of structures and look at how the peak pattern looks. So, in the next class we will move on to HMQC, which is another experiment very similar to HSQC, and then another experiment further is HMBC, and that will tell us how the different experiments work. As we saw, in HSQC is not sufficient just for assignment, HMBC helps sometimes when there is an ambiguity, and that we will see in the next class.